So today we're going to be talking about a concept, an important concept called differentiability. When is a function differentiable at a point or on an interval? And that just means that it has a derivative, that you can calculate the derivative, or the derivative is equal to a real number. Okay? And I wanted to back up just for a moment and remind you about the difference between, or what we talked about last week, I should say, continuity, where continuity at a point where the limit exists, the function exists, and then the limit is equal to the value of the function, therefore the function would be continuous. Well, differentiability is related to continuity, but it's not always the same. In other words, just because a function is continuous doesn't mean that it's going to be differentiable the whole time. So probably the best way to describe differentiability in layman's terms would be the analogy of a train, and I think it says that somewhere in here, but if the train is traveling on the train tracks need to be nice and smooth. So you want to think smooth and continuous. If you have sharp points, then the train is going to become derailed. Okay, I mean, you don't normally see train tracks that look like that, but nevertheless, there are curves in train tracks, and trains can handle that, but they can't handle things like you go up here and then sharp turn. The train isn't going to be able to stay on the rails. So keep that in mind in terms of layman's terms. And we'll get to the actual definitions and the technical jargon, but let's go ahead and take a look down here. I think you could probably, just based on what I said, determine which tracks the train would stay on and which tracks the train would become derailed on. This would be, let's see, so example, determine whether the following functions are continuous, differentiable, neither, or both. So this would be not continuous here, and so since it's not continuous, you could see the train would jump the tracks there, so it would be neither. Neither continuous nor differentiable here. Okay. Over here, it's not continuous, and the train would become derailed there. Any holes in the tracks, the train's not going to stay on the tracks. So this again would also be neither. Okay, now this one, continuous here and nice and smooth, so would be both continuous and differentiable. So you might be thinking, well, what would it look like if it were continuous but not differentiable? Well, that's right here. So here you have a straight line connecting with a curve, so this would be more than likely a piecewise function. And we have a sharp point right there. So it's, although it's continuous, it's not differentiable. So you would not be able to calculate the derivative at that point right there because it's a sharp point. Okay, and then over here D, we've got a discontinuity here at this vertical asymptote. So it would be neither continuous nor differentiable. And here we have a sharp point. So maybe you do the rest of these, okay? Tell me what this would be, and then do G and H as well, and then play the video. So here we have a sharp point. It's continuous, but not differentiable. Okay. And then here again, it doesn't have to be much of a sharp point, but again, that is continuous and not differentiable. And this guy here, it looks to me, and they didn't make this super clear, this worksheet, but it looks to me like we might have a vertical tangent line. Okay, and keep in mind, the derivative at any point of on the graph would be the slope of the tangent line to that graph at that point. And so if the slope of if the tangent line is vertical, then we would say then the derivative wouldn't exist. So that's like the last piece to the puzzle. If the function is not continuous, it's not going to be differentiable. Okay, if it's got a sharp point, it's not going to be differentiable. But the last one would be if it has a vertical tangent, then we would say that the function is not differentiable at that point right there where the vertical tangent exists. So we would say this one also is continuous but not differentiable. So there you go. Now, let's look down here. We've got 4 more examples down here at the bottom where you're not given the graph, obviously, we're just given the function. And your knowledge of function is going to help you here. Okay? You know that this being a polynomial function is continuous. Okay. You also know that polynomial functions are smooth, so it's also differentiable. So I should have said both. Okay. Over here, we know we can factor the numerator x minus 4 times x plus 3. Your knowledge of discontinuities would allow you to see that here we have a discontinuity at x equals negative 3. So that means not continuous. And if it's not continuous, then it can't possibly be differentiable. Because if you don't have a continuous track, then the train's going to run off that track. Okay, so anyway, we have a hole in the graph because we know we can cancel the factor, and therefore it would be neither continuous nor differentiable. Now we know the graph, the sine of x, looks like that, nice and smooth through the whole, for the entire domain, so we would have both continuous and differentiable. And then sine of x over x, here we have a discontinuity at x equals 0, and we can't cancel that factor, so it's an infinite discontinuity. And if we have any discontinuities at all, we know that that would represent a place where the function is not differentiable. So we would say neither continuous nor differentiable. So let's just go ahead and review now the actual rules and the definitions so you can have that. Good knowledge of that. Differentiability at a point. Okay. If and only if f prime, that's basically what we said, differentiability at a point, f prime at c exists. Okay. On an interval, if a function is to be differentiable on an entire interval, it means that every point on that interval, the function is differentiable. Okay? And differentiability, I got to be honest right now, I don't have my glasses with me, and I'm struggling to see these things, so I'm not even going to try to read that one. Let's look down here. Read this. Concept means smooth, so we talked about that, so I'm able to pick out a few words here. No sharp points. Where is it? And then, so in class we can look at a cusp or a just a kind of sharp point. You can call it a sharp point even if it's a cusp. So basically it's a sharp turn in the graph. Or where the tangent line is vertical. Okay, so no sharp points, cusp, tangent line vertical, but also it must be defined at every point on the interval. So in other words, if a function is to be differentiable, it must be continuous. Okay, and that's important to understand. So if you need a function to be continuous, you can say, oh, you already know it's differentiable over the entire interval, so therefore the function would be continuous. And but that doesn't work the other way, just because, and we've shown that already, continuity does not imply differentiability. Okay, so I'm going to start a new video and do the second page, and then we'll be done.